Very good morning to all the ladies and gentlemen who are present here on the day 3, session 5 of National Workshop on Advanced Synthesis and Characterization Techniques, organized by Department of Applied Physics, MIT School of Engineering and Technology, MIT University, Madhya Pradesh. Today, we are honored to have with us Dr. Jay Singh, who is working as Associate Professor in Department of Pure and Applied Physics, Guru Ghasidas Vishwavidyalaya, a central university from Bilaspur. Before he will give you his precious knowledge, I would like to give his brief profile. Dr. Jay Singh has research and teaching experience of more than 16 years. He has worked as scientist in Department of Physics, Banaras Hindu University, Varanasi, India, for the topic hydrogen, for the area hydrogen storage materials and oxide nanomaterials. He has also worked as visiting scientist in Institute of Inorganic and Material Chemistry in Cologne, Germany on transparent conducting oxide. He has experience of postdoctoral fellow in School of Material Science and Engineering, Busan National University, Busan, South Korea, while he has worked on transparent conducting oxide, oxide thin films, and graphene. He is also having experience of research professor from Graphene Research Institute, Department of Physics and Department of Nano Engineering, Sejong University, Seoul, South Korea, where he has worked in the area of graphene and oxide film. He has published more than 68 papers in reputed index journals, several book chapters, and many international national conferences. He has 1,350 Google citations, H index for 25, I-10 index 43 in his name. His area of interests include synthesis, characterization, properties and application of different metal oxide nanostructures, thin films and its nanocomposites by employing various techniques. He is having professional expertise in synthesis methods, characterization techniques, properties and application measurement tools. Apart from this, he is also working as editorial board member for various reputed journals, like editorial board member for International Journal of Ceramic Technology, International Journal of Alloys, International Journal of Bionics and Biomaterials, and many more. He has also completed DST Fast Track project on the topic synthesis, characterization, and application of bulk nanostructured thermoelectric materials as a foundation of sustainable energy. Also completed project on UGC startup grant for newly recruited faculty title for project is growth of large area, highly crystalline single layer MOS2 thin film on insulating substrates for transparent electronics. His resume does not end here. He has received several awards and recognitions, including NET-JRF, SRF, GATE, JEST, Visiting Scientist Fellowship by Institute of Inorganic and Material Chemistry, Germany, Busan National University Postdoctoral Award for Postdoc. So with this, I would like to invite you, sir, for the topic scanning electron microscopy, transmission electron microscopy, and energy dispersive X-ray analysis. Please, sir.
Thank you very much, ma'am, for your kind introduction. Basically, you have read my CV very old. I think 5-6 years old CV. Don't worry. Okay. Today I will discuss about especially on scanning electron microscopy, and little bit I will transmission electron microscopy. If time be allowed, then I will discuss energy dispersive X-ray (EDS). This is another techniques. And before this, I want to share simple physics about this instrument. If you know about the wavelength lambda is equal to S P, and P is momentum, and P is equal to M into V, and V is velocity of the system object, and that velocity is also connected the half mv square ev. That is the whole thing will be interconnected with the your quantum mechanics lambda is equal to H by inversely proportional to B. When then potential will be increases, your wavelength will be decreases. The simple phenomena and the simple physics that we will use in during the discussion, and that will be used for the scanning electron microscopy as well as the transmission electron. In during this talk, I discuss about the what can we use for scanning electromicroscopy, how can get the image, and the most important things is the electron beam interaction. There is electron and matter interaction. What will be happen? Which types of phenomena will be occurred, and that which type of signal we can use for the characterization of the your surface. Basically, there are two system. We will use the secondary electron as well as the back scattered electron, especially for the SEM. In a TM, we will use only transmission electrons. Then I will describe in detail. Don't worry about this. And then and also we will discuss about the component of the your electron microscopy and some comment on the resolution as well as the energy dispersive X-ray. Then time will be allowed. Then I will discuss. Okay. Most important things is what is microscopy and how many types of microscopy. Microscopy is nothing. Microscopy techniques that can be, we can see the object, we can in the as though we can anyhow we can magnify your object by the different methods. There are three types of main microscopy is available right now: optical microscopy, electron microscopy. Third one is the scanning probe microscopy. Optical and electron sometimes that be like this similar, but scanning probe microscopy is totally different. Microscopy, there is involved the interaction of the scanning probe on the surface of the object. That's the word in AFM. I think on 14, Dr. will be discuss about this scanning probe microscopy, atomic force microscopy. They will cover. Then you can know about the whole things. In optical and electron microscopy, that will be involved. There is simple physics, diffraction, reflection, refraction, and the radiation of the incident of the your object as this collect this scattered radiation order to build up the image. That means is we will build up in different manners. So that is first we know about the optical microscopy. Optical is nothing that we will use the light source, visual light. Visual light, you know, the wavelength is nearly 400 to 800 nanometers. That we will use the lens, and with the help of lenses, we can magnify our the sample. The same you have used the hand lens that you can magnify your the object for the you can see the any small part of the writing, anything you can with the help of you can magnify. Same things you can use the optical microscopy that magnify your object, your as like bacteria and many more things. Then you can visualize very simple manner. Okay, that the whole object, whole image we can find out in photography plates right now. In you can also capture by digitally. Right now we are living in the digital, so we can also use the in JPG and PNG form. So there
Excuse
are
me, sir.
lenses. Hello,
Uh, sir, your slides are not moving.
is not moving.
Yes, sir. Still, it is on the
Okay,
introductory slide.
1 minute. Now moving.
Now we are on the optical microscopy. The slide which is
Okay,
visible
okay.
is optical microscopy.
Sir, have you done a slideshow mode?
Yeah, I'm.
Yes, sir. Moving now.
Now it's
Perfectly
moving.
Uh, this is next slide. You can see optical microscope scheme.
Yes, sir.
No, still it is optical
One is the
microscopy.
optical limitation.
It's still optical microscopy.
Optical
Okay,
microscopy is there, sir.
okay. Only basically in if I will go in a slide show mode, then that cannot though. In the second slide, you can see.
Yes, sir.
Yeah,
Okay,
Optical
so that is
microscopy
shown
limitations
in
are
the.
there.
Okay. I think, okay. Okay, my system is not allowed for the full screen, so I will discuss only in this mode. Okay, sorry to that. Uh, okay, then I was discussing about the optical microscope. Here you can see the optical microscope scheme. There is some lenses. There is the eyepiece tube and objective lenses. There is the different magnified some 20x, 50x, 100x that we can use for the magnification of your object in the with the help of only your visual light. Okay. This is the what is limitation behind this optical microscopy. There is several version and as well as the several things will be occurred during the optical microscope. Basically, if you think about this is the some what is the limit of this optical resolution. There is simple formula D is equal to lambda by an. This lambda is a wavelength of your optical light. Basically, that if you think about if you take this green light is wavelength nearly 550 nanometers, and this is the an. An is the your means that will be numerical aperture. This value will be for the air nearly 1, and as well as for the your IL 1.5. If you think about if you use only in presence of the air, so D is equal to lambda is equal to upon 2an. That resolution is only the maximum resolution you can get the only 200 nanometer, means only 0.2 micrometer we can visualize. We can find out the limitation of the behind this. Basically, we cannot see the only the nanoscale or angstrom level. We cannot see the atom level system with the help of this optical microscope. For this, we need some different type of microscopy. For this, that we will discuss about the your scanning microscopy as well as the transmission microscopy. What is the resolution and resolving power? That this is the ability of the lens to separate the distinct small object that will be close together. Then if you use the shorter wavelength, that we can get the greater resolution. That behind this we will use this electron microscopy that is developed in the 1930. And there are two types of electron microscopy, as I told. This is first one is the transmission electron microscopy, and second is the scanning electron microscopy. In a transmission electron microscopy, that will be see the only, we can choose the only thin, very thin slice, and that is slice thickness is the less than 100 nanometer. And if you take the more than 100 nanometer, that electron will be completely absorbed. That we cannot observe, we cannot find out the full image, internal image of the your materials as well as the. And in a scanning electron microscopy, that we can see the 3D images, and that will be also visualize the surface of the cell in the quantity and qualitative manner. That magnification is definitely lower than the transmission electron microscopy, but there we can use that for different manner and different in situ experiment, and many more types of experiment we can do in the scanning electron microscopy. Okay, you can see here with this cartoon there are three different light microscopy, transmission microscopy, and scanning electron microscopy. Light microscopy and transmission microscopy looks like a similar, that we can put the same place the specimen, and basic difference between the electron microscopy and light microscopy. In a light microscopy, we use the lenses, that is the glass lenses. Glass lenses, condenser lens, and eyepiece lenses made by the glasses. But here in a electron microscopy, any transmission as well as the scanning microscopy, that we will use the lenses that is known as the electromagnetic lenses. That is very interesting. That is the virtual types of lenses. Only with the help of the magnetic field as well as the electric field, we can control your electron beam there with the help of very simple physics, 10+2 physics. That will be, you can accelerate your electrons with the help of this this is electro optics that is system. Both in the light microscopy and transmission microscopy, your specimen is the completely thin, that your system will be your electron as the light will be transmit with your sample, that it transmitted sample with the help of, we can magnify by the different manner, different methods, that we can find your images. But in a scanning electron microscopy is totally different, that matter will be interact with the sample, that there are several phenomena will be occurred. We will describe in next slide, that electron will be interact with your sample. Basically, in a scanning microscopy, that we have two types of electron will be used, the back scattered electron and secondary electrons. That will be, we will use that both electrons for your find out the image of your object. So with the help of there are several things, a detector as well as the many more part will be attached with this scanning microscopy. After that, we can find the final image in this. That in a scanning microscopy, that use the focus probe to extract structural and chemical information, but point by point from the region of the interest of our samples. We can select the with the help of probe, we can 10 nanometer to 100 nanometer area. With the help of then scan by point, that system will be scanned and find out the overall find out the image of your object. And that will be resolution of the same, make the very powerful tools. And also that will be, we can find out the nano region to micro region length scale. We can find out the your object. That this, with the help of this cartoon, we can find out the limitation of your eyes as well as the light microscopy and electron microscopy. If you see any object, then in a micro level, that is the only you can use the light microscopy. But you find out, you can see any atomic level system, the atoms as well as the virus, that we cannot see by the light microscopy or naked eye. So for this, we use some special type of microscopy. Without electron microscopy, we cannot observe the behavior of your virus as well as your atoms behavior, atom size, and many more things, and lattice, planes, defects, impurity. Without electron microscopy, we can not observe with the atomic. You can see here the market value of this scanning microscopy, that is growing very fast. Right now, $80 million right now is the market of this scanning microscopy. You can see here very beautiful hair of the woman. That is in India, obviously nearly 2,000 crore INR crore is in the industry, that is still keeping very growing fast. For this beautiful hairs, that we need the quality and quantity, and for this people are using the scanning microscope. Then with the help of this, you can find out your at the micron level which types of that material your hair looks like. That hairs is, you can see here, hairs is looks like there is several steps, and that with the help of then pricing and many more things, that will be depend upon the quality of hairs and many more things. So that is very also important for the many more dermology and many more research point of view. In this cartoon, you can see this is coronavirus. The real image of this coronavirus is that is taken by this transmission electron microscopy. This is not a scanning microscopy. That this is looks like at a nano region is looks like in second is yellow, and this will is some manufactured by the different method. What does it looks like at a nano scale? And that if you think about the atomic force microscopy, cantilevers looks like very sharp, and ant headed looks like in this slides, and blood cells looks like some pills, and many more diamond like than diamond thin films looks like. And at this, the whole image is the only at the this is the nano range. So at the nano range, that will be looks like totally different as well as the micro as well as the in bulk region. This is the history of this scanning microscopy. The first I want to describe here. First, Ruska was developed in 1935 TM. After that, in 1965, the SCM was customized very later, very old, and in 1985 that will be described the atomic force microscopy. So I want to say here is the more complicated instrument was discovered is the very early in 1930, and least complicated instrument is the AFM that will describe is the 1985. So only if you know about the basic physics, about the how to utilize the physics, how to utilize the science, that we can find out the cheaper and cheaper and quality and better quality instrument. So that is the right now, the quality of the SCM instrument is very high, that we can use the environmental SCM, FESCM, and many more systems that can utilize for the in-situ experiment and biological sample. So right now is the TEM is a totally analytical instrument that can utilize for the any solid, liquid, gases, and life science people, geology peoples, and physics people, chemistry people, any people can utilize for the different orientation and different work. And right now, resolution is less than 1 nanometer. That is one of the best achievement in this instrument. So there are several Nobel Prize was owned by the different groups. That in 1986, that Ruska was awarded Nobel Prize in Physics for the development transmission electron microscopy, and many more, and another microscopy, atomic force microscopy. That is the that Bini group, and was the that they got the Nobel Prize in the and. This is very earlier 1915 microscopy. You can see this is a very big microscopy, is bigger than room size, is a classroom size. And right now that we have achieved a very small size, nearly 5 by 6 foot is enough for the spacing for the this electron microscopy. This is the scanning microscopy that we install in our institute. That resolution of this instrument is nearly 2 to 3 nanometer at 30 kV. That we are using the different types of filaments that I will describe where is that we use the filament and how that will be work as the filament, and which type of physics is involved. This is another types of this is scanning electron microscopy is that in some is very old, some is very new, and that people are using for the imaging. This is, and there is a different, there are 3 leading companies, JAIS, FEI. FEI is, I think, sold by the Brooker, and many more companies that will be, and Geol, Oxford, many, several companies are making this SCM. And this SCM is a FEI that is installed in the in Sagar in Central University, I think, in Madhya Pradesh. Okay. This is some beautiful image you can see here. This is at nano region. That is the nano flowers, nano rod, nano beads, nano tube. That is whole things will be without the SCM we cannot see at the nano levels. If you that is the whole bulk sample is looks like the black or white. When we go inside this sample at the nano region, that we found the beautiful I think you can say the natural things about the flower like structures, nano tetrapod like structure, nano rod, many more things, several other types, nano bottles, nano combs, many more types of structure you can see. I will slow this slide very fast. This is a nano. This is this image is developed by the PLD. I think Dr. Anupama Chandra here described about the PLD. That sample is grown by the pulsator systems in a silicon substrate at different temperature. So whole things, if you know about the mechanism about the your our growth morphology and many more things. If you want to describe about this, so you need the same images and transmission images at different temperature, different time, different pressure, and several parameters you can choose, and then you can prepare your sample that you can fit you can give uh, mechanism behind this. There is some science behind this another beautiful image, the nanocombs that is made by the this is only physical vapor deposition system, and this nano nails and nano kites and nano tubes and different is this is a one wonderful another structure is this is a new perovskite solar cell is the new solar cell material. This is AB3 types system, and this you can see looks like this cubes and nano beads, and this under carbon nanofibers and carbon nanotubes, graphene. This is a TM images as well as the SEM images in this that is prepared by the hammer root and as well as the modified hammer methods. And this is a wonderful image that the all images that will be developed by in my own labs. And this is not my own lab. This is the same image, the gallium nitride. This is a yummy beam, molecular beam epitaxy by method that was developed by this images. And most finally we come to our topic. What can we study in SEM? First, we find out the topography and morphology and chemistry and crystallography, orientation of grain, and most important, right now people are using the in situ experiment. If you want to your high impact factor paper that everybody doing the research on in situ experiment, the reaction at the different atmosphere and effect of temperature, and the same simultaneously we can see the image as well as the whole things. So that in the basically in a SEM is you very easy to prepare your sample, and you can also use the sample nearly is the inches size, but in a TM you can use your sample only the less than 100 nanometer. That is one of the bigger difference between the both instrument. And also, topography and morphology, that is that is the qualitative and quantitative things. And the most important things, the depth of the focus is very high compared than optical microscopy and any types of microscopy available in the market. That depth of focus is very higher, and that we can see each and every types of planes and grooves and many more, any striking fault on that is the which types of your crystal are growing. So that will as the nano region we can find out that this is the qualitative and quantitative image. What is the behind the difference between your topography and morphology? Morphology is basically this is the qualitative types of information we can find, but in a topography that we can find the qualitative information, that with the help of that we can find out here we can see that this is your depth of focus. The first one is this is the optical microscopy image, and second one is the scanning. In a scanning microscopy, we can see every grooves at the deeper level. That is we can find the every very beautiful information, very for your any detailed information with the help of this scanning microscopy. This is another image of this is the first one is looks like blur image is the optical microscopy, and second is the scanning electron microscopy that we can see that if you want to deeper and clear image, that with the help of this scanning electron microscopy that you can find some beautiful image. This is some coil. This is looks like carbon fibers, and this is the upper image is the scanning electron microscopy. Lower image in the optical microscopy that you can see here. That in a scanning microscopy we can get the clear information. That is one. That is this modern SEM equipment with the accessory with the hot stage means we can give some temperature of your sample during the imaging process. This is known as the in situ experiment, in situ process of your system. And This is the one of the chromium oxide sample that you can see here that at 800 degrees centigrade temperature at different times. Here we can find out the, if you put your sample at, that is called the handling sample, or any types of processing system at a different atmosphere, different temperature, different pressure, that you can see the how to system will be nucleate at with respect to with respect to your times. As well as also you can see the this type of images at different time, 600 degrees centigrade, 700 degrees centigrade, 800 degrees centigrade, which types of your chromium oxide, yeah, steel or copper, any more complicated your gold, which types of behavior will be find out during the this in situ experiment. So how the SEM work? SEM use the electron, as I told you, instead of the light, and beam of electron produced by the top by the heatium of the metallic as well as the field emission. There are two phenomena: thermionic emission as well as the field emission phenomena. Thermionic emission is the classical phenomena, and field emission is the quantum phenomena. An electron being allowed in the vertical path with through the column, and that whole thing will be controlled by the several that will be part will be available in the column. There is the some aperture as well as the lenses, optoelectronic lenses that will use as like your light lenses, your lenses, real lenses, your conventional lenses, objective lenses, that will be the whole that will your electron beam will be passed with the in between your electric field as well as the magnetic field. So that after that your electron will be interact with your sample. There are production of the secondary electron and backscatter electron, and also that your system will be your produce the X-ray electrons. That finally this is a simple thing. This is a column you can see here, and in this column there is upper part is the your electron source. There is people are using LaB6 or tungsten, and in upper lower part is the that specimen chamber is very big, that you can use the sample nearly 18 sample is that you can means you can use your sample is the micron size as well as the 18 sample, that is that bigger sample you can use the. And there is two types of detector we are using, basically secondary electron detector and backscatter, both are there. This is the basic image here, when how to electron will interact, and after the interaction that electron will be out and X-ray will be out. That will be, you can see here, there is a clear image. Please concentrate on this slide. This is your main, this is the red is in your basic, yeah, primary electron beam. When a primary electron beam will interacted with your sample at different your sample will be interact at different level. That will be first will be at when you got the information as the only the nano region with the help of secondary electron. If you want to get the more deeper information with the help of backscatter electron, then we can get the your X-ray EDX information nearly 1 to 3 micrometer. And if the sample will be transmit, your electron will be transmit, that will be, you can use the transmission electron microscopy, and but we need the your sample will be very thinner, less than 100 nanometer. If your sample is the thicker, the whole phenomena will only this type, and another phenomena will be also cathodoluminescence phenomena will be that people are using optical material research. People are using the they are using the whole things will be in situ experiment in the SEM cathodoluminescence for the imaging of that your skin, many more things. So another this is one of the beautiful image. This is the understanding of the principle. There is the electron and matter interaction. That when the electron will be interact with the matter, there are several phenomena will be occurred, but I am interesting only the backscatter electron, secondary electron, and transmitted electron without interaction, that will be, but with that will be interaction will be some, then we find the diffraction of the electron in elastic and inelastic, that, and that is the X-ray. So there are four types of that will be of the interaction. We are interested back excitated electrons, secondary electrons, as well as transmitted electron and X-ray electron. The whole things will be used in the scanning electron microscopy, transmissional microscopy, as well as the EDX microscopy. EDX, that is not microscopy, this is the energy dispersive X-ray system. So you can see here very beautiful image that with here how the electron we can find out the from the your sample. Basically, I cannot see. Basically, you cannot see here your in the full screen. So we cannot you cannot get the more and more information. But I will give basically that scanning anoscopy that we collected. That you can see there are several blocks in a square form. That is sometimes we can say that is a pixel. That is a different reason. Basically, we can collect the different number of electrons. Basically, you can think about the your hand is your sample. Then you can see your hand. There is here that is your skin will be looks like sometimes your different heights. So that will be with if you use your torch as a light source, that will be find the your light will be transmitted at the different region is the different amounts. So whole things will be is the behind the same phenomena will be occurred here when will be your interact your sample with the electron beam. There are different number of electron will be generated at different points, and this different number of electron will be collected by your detector. That detector is the there a limitation. If you use the secondary electron, that will detect the different number of electron, yeah, different number of energy in a form of energy, and the same if you use the back excitated detector, that will be collect the different number of electron, a different number of range of energy. So that is the range of energy that we collected by your detector. After this is the with the help of this imaging processing, and that we can find out this is the with the help of this signal in the transfer in image, and that with the image you can find you see the nano flower, nano rod as like that. So then at different point you can collect the different number of electrons. With the help of different number of electrons, that will find out with the imaging processes we can find out the final structure of your object. Or this is a brief. This is a cross sectional view of your scanning electron microscopy. That is the upper part is the electron guns, and intermediate is the gun alignment, and the third one is the airlock valve, and fourth one is the condenser lens. Fifth one is the objective aperture. With the help of then you can tilt the electron beam, and fifth one is the scanning coils, and seventh one is the objective lens, and last one is motorized stage. That with the help of motorized stage you can tilt the electron at different angle, and last one is the sample stage. This is the cross sectional view of your scanning column. This is only column, this is not whole instrument. And lower part is there is vacuum system. You are using there is turbo pump, is the many more types of pump are using for the vacuum system, and many more other system. This is another view of this is a cross-sectional view of this is the whole system: scan coil, sample stage, detector, vacuum system, computer, hardware, software. This is a whole complete SCM system. The most important is the filament, and this electromagnetic optics, and scan coils, sample stage, detector, vacuum system. And that is the last is the hardware and software that you utilize for the find out the final image of your object, and many more. And how to that we can magnify, and this will control your beam as well as your other things with the help of this condenser lens, and your electro-optical lenses, and with the help of that you can also we can collect the sample with the help of amplifier. This is the PPMT types of amplifier, secondary electron, back escalated electrons, and that there are two types of detector we use, and that. So there is some basic physics about this, how to work your scanning electron system, and this how to work use electrostatic lenses, and the transport charge, how to there is very simple physics. Physics is only when the charge particle is moving in the uniform magnetic field, and uniform magnetic field, then you can find the helical path. And only with the help of this only simple physics we have the different potential V1 and V2, and with the help of this V1 and V2 we can tune the your path of the electron beams, and with the help of that we can find out that is simple, that you can see that with the help of Snell law, sin I by sin R is equal to N2 by N1. This is N2 by N1 is the reflective index of your object, means your one medium to another medium, and this N1 by N2 is equal to, this is a V2 by V1, and that is also, this is psi I1 by psi R is equal to, this is equal to V1 by V2. This is similar in an electron beam, can be accelerate or retract, de-accelerate of your electron with the help of this electrostatics and magnetic field, and that will be, you can, as like the ordinary lenses, your electron will be deflected as well as the your reflected from the your normal lines. Behind only this, then you can choose the area, how much area, if you choose the micron size as well as the nano size, only with the help of this the control the simple physics, and that I have already discussed about half mv square is equal to EV1, and V1 is equal to, this V1 is the velocity of the your electrons, and that will that will be V1 by V2 is equal to is a under root potential V1 by V2. Bigger V1 V2 is the potential, nothing else. This psi 1 I by sin R is equal to velocity of the your electron beam V2 by V1 is equal to, that is the, also you can see here that will be inversely proportional. This is the under root V2 by V1. V2 is the your potential at the upper point, and this V1 is potential at different region, and that for this, if the V2 is the bigger and compare than V1, the beam is reflected towards the normal lines. That is very simple. And when V2 is lower than V1, the beam is deflected from the normal, similar to reflection of the light. So with the help of this acceleration of the electrons by the controlling of this, also this, with the help of this potential V1 by V1 V2, that we can also the magnify, or we can change the wavelength of the electrons lambda, that so whole things will be completely depend upon the your this with the your potential V1 V2, and we can accelerate and de-accelerate of the electrons as well as the, so if you with the help of this simple knowledge or simple physics, then you can find out the how to control the electron beams, how to take the path of the electron beams. So another basic science, basic physics, this half mv square sin theta is equal to R is equal to this B cross B, this with the help of, then also we can take the time, take this electron described by the circle, that the whole things, the electron, the process with the component of the what in the helical path as well as the straight line path and circular path, only the controlling of the your electric field as well as the magnetic field. So that will be, and also we can control the your current with the help of this This is this is your looks like this electrostatic lenses as well as the light lenses. You can see here there is the behave like the same types of, there is the charged particles is the when in a different potential V1 V2, that will be if the if you use the real lenses and different medium, this is a reflective index N1 N2, and that will be your rays will be behave like the same as like your is the charge particle behave like. So this is under this electrolysis lenses. Then we can use the different cylindrical tubes, and that will be you can. So there is which types of, there is the some lenses. This is a virtual, as I told you, that is virtual lenses. Virtual lenses is made by the iron and copper. This iron and copper, this is iron. This is a different ball size, and the next slide you can see here. This is a soft iron is the upper side, and copper coil is the inner side of the your this virtual lenses. So this lenses, this with help of this, both are the your behave like the magnetic field. This iron is also, you can know, very good magnetic materials. Copper is also very good magnetic materials. So that your electron beam is the when we transmit your in the magnetic in the electric field, that electron will be taken the path like the helical path, looks like here, that we can control our the beam with the help of this only this lenses. This is called the electro-optical lenses. This electro-optical lenses are made by the iron and the your copper. And iron, as you know, this is made by the magnetic. This is the easily we the North Pole and South Pole. So with the help of this, we can the same optical lenses work like so. That is the magnetic consists of this coils copper wires and iron pole pieces. So there you know very well, this is Lorentz force F is equal to E small e capital E into E V cross B. So that will be the whole things. F is equal to E V B sine theta, and sine theta is the totally depend upon the velocity of the magnitude of the your magnetic strength as well as the and your that will be electric charge. So that will be with the help of this Lorentz force, or that electron will be feel the experience, and that electron path will be depend upon the so this another important thing that you can see here, when your material will be interact with the sample, that will be when we are using the low accelerating voltage, your material will be interact with the only the upper layer of the sample. When we give the medium acceleration, that will be go the deeper side. When we give the higher acceleration voltage, that will be means higher acceleration means velocity will be faster. That will be sample will be interact with the deeper and deeper side. The same things will be happen when the change the when the your material will be with high atomic number. That will be your material will be give the more and very better and better information. Means you need the lower acceleration. Lower acceleration is good for the higher atomic number materials. When you have the lower atomic number system, that we need the high acceleration. Means if you had the tungsten and any silver, gold, and this types of material, there is enough to 5 electron volt is the very 5 volt is enough. But you need the some copper types or some sodium, magnesium. So you need the very high 30 kV electron volt is the if you need for imaging process of the your samples. So that it totally depend upon the number of atomic number available in your sample, and which type of sample you are using. If for the sometimes if you are using the some special types of materials, some polymers and some non-metal insulator type system, then we coat the some gold or silver upper surface of the. Sometimes people are also using the platinum. And but gold and silver is enough for the find out the very good image. Only for the some I think only angstrom level is enough. I think 1 nanometer is very good for the imaging of the this process of the this system. Behind this that is the atomic number as well as the acceleration of the voltage is a very important parameter for the find out the whole thing. That is also already I have described, so I don't want to discuss about detail about this. This is the how to generate the this is the your secondary electron as well as the your back scattered electron. So that is the first I will discuss the secondary electron. Sometimes also called as the SEM is the as like the secondary electron microscopy. This is the generate from the collision of the between the incoming electron and the your loosely bound your electron. Basically your if your system have the atoms, the molecules, atoms had the some electron will be revolve in the outer side, and inner side that will be nucleus at the neutron proton. So upper side are any loosely bound electron that will be easily that will be transmit from the your system, and that with that energy is not very high, only 30-50 electron volt is that will be generated, and only 10 to 50 electron volt that we use the special types of detector for the only this range that will be detect the electron. So in the both detector, the secondary as well as the back scattered electron, we can use the both are different types of detector that people are using in a scanning microscopy. So only secondary electron close to the surface that will be easily that we use the topography information that will be qualitative information you can find. And also that secondary electron with the two types of secondary electron 1 and secondary electron 2 types of. And secondary electron 1 is that will be generated by the incoming electron beam that will be enter the surface, that with the help of if you find out the high resolution signal and resolving when better and better, that will be we can use the secondary electron 1 for this purposes. And this is secondary electron 2 secondary electron 2 that will be completely work as a term completely different. That secondary electron are generated by the back scattered electron process, but that is not as like back scattered. That is the back scattered generation of this electron is back scattered from, and that will be and incompletely after the inelastic scattering. In a secondary, that will be elastic scattering. So there is one main difference between secondary electron 2 and back scattered. So, and secondary electron 2 comes from the surface area, that is the bigger, that will spot from the incoming electron. Resolution is poor, basically that will cover the more and more area, and compare than secondary electron first. Secondary electron first is the that will be that electron will travel very less area, less that will cover very less focusing very less point, are that incoming electron will travel very low distance. So I think that the sample that we can get the very high quality of resolution, but in the secondary electron 2 that we can find the that will be that imaging process is, the resolution is not good compared to secondary electron. And that is which type of factor that we affected in the secondary electron, that is the work function of the surface. That is also important. Basically, as I told you, there is some filament about the filament. Filament people are using the tungsten and LABCs, and the both system will be choose only the reason is the work function as that, and also the high melting point of that system of the materials. So if you use the thermionic emission as well as the field emission, so both material is good for the, and also another parameter is the work function. And beam energy and beam current behavior, that is also a reason behind the choosing this system. And another effect, the parameter is the atomic number of the samples, and that is if the more secondary electron are created by the increasing the jet, if your system having the higher jet, that you can that secondary electron 2 is more and more. So Z is also important parameters that you can generate it, and also means that you can use the lower energy that you can find the better and better images. So and high resolution image setup that will be by the placing the secondary electron detector inside the lenses. Mainly secondary one are the detected, and secondary one resolution is the we can find the 1 to 2 nanometer is possible for the with the help of secondary one electron microscope. And second is very important, the back scattered. Back scattered is work as the completely and elastic scattering of the factor of this incident electron is the retorted by the electromagnetic field of the nucleus completely 180 degree scattered the angle, the electron can be escaped from the surface. And after that, your system will be generated the back scattered. That's also called, this is the name of the back scattered. So completely 180 degree that will be transmit, and that will be, and the high energy electron that will completely, as I told you, elastic scattering, and Se2 I think you remember, that is the inelastic scattering. And but in the back scattered, we can find the fewer number of electrons compared than secondary electrons. And also back scattered is also two types, back scattered 1 and back scattered 2. So I'm not going to discuss in details. So please escape. That is not also with the EDX energy dispersive spectra, yeah, EDX energy dispersive X-ray. So there is many more things about involved here. Dead time, statics. There is a signal to noise ratio. How to remove this point and drift in the electron beam with time. So there are many more things considering for the energy dispersive. There is EDX patterns. And if I have some graph, then I will show. Okay. There is no need. Okay, there is, you can see here, this is a lower image, is a secondary taken by the secondary electrons detector, and first one is the back scatter. So then there is first image is looks like blur. So if you secondary electron is good for the topography for the this processor. Okay. Here you can see there the other parameters that will be involved in the this if you increase the current of the your beam, that is the beam is some picoampere different times, and that will be you can find. And then you can see first one is the 10 picoampere only for 10 seconds. There is looks like some blur images when 10 picoampere, but time is increases, that looks like some better and better images. When we use the 100 picoampere and 160 second, that will there we can find the very small noise, and resolution is very better, and then we can get the very more clear and more deeper, more informative from our sample. So that and also that will be noise is very less. So in ADX is also very important parameter, dead time and noise and many more things that we can collect. Basically that is there is several I think so moistures as well as some air contamination. So we need some high vacuum as well as for the higher current and for the higher times, that you can get the better and better result from your sample. So there are some more. This is the already discussed. Don't need to. Okay, no need. Okay, so another important thing is the just I want to describe. This is the electron guns. Okay, many electrons. Basically, we need the I think huge number of electron for the imaging processes. So electron per time per area, that is the need the high current density. So for the high current density, and also that will be we can control this current density with the several optical lenses and aperture. So and traditional is the best, as I told you, Fermiani electron gun, and that is very simple. Please after sometimes after 30 minutes. Okay. Please. Sorry. This is the thermionic emission. Only this is nothing. This current density J is directly proportional to T squared temperature. And what is the modern times we are use the field emission gun. This is also known as a cold gun, as a field emission. There is that E is E. I think E is equal to and also that is the current density. J is completely dependent on the electric field. So that will be right now people are using some different nanostructure for the this electron that for your imaging purposes. Some people are using the carbon nanotubes as well as the zinc oxide wire and rod for the single crystal types of tungsten. For this, basically, if you use the better image and high quality image, that you need the field emission gun. Okay, I think this looks like electron gun is, you can see here different. This is the first two. One is the your thermionic emission gun, and second one is this tips like is the your field emission gun. This is the field emission tips. Okay, and next one is the how to that electron gun is work, and that will be that will be electron will be generated. Okay, don't need to in details, and that is some basic difference between the kind of electron gun. If you use the tungsten hairpin, LAB6, and field emission softy types of there you can see here, if the tungsten types of that we can electron source diameter is the only 30 micrometer, and that is that electron source is very controlled in a 10 micrometer. And that is in a field emission, electron emission is gun is the very sharp, find 5 nanometers, that we can find out the better and better image information and deeper profile. And brightness of this in the tungsten means thermionic emission 10 power 6, but in a field emission 10 power 9. And energy bit is the 2 electron volt, and here is the electron is the 0.2. And also most important is the life of your system, and a cathode life is only 15 hours, but is the field emission is the 1 hours. But cost of this system is a more higher. The cost of the nearly and $10, but is the field emission gun is the $100. That cost is also very higher in the field emission. That people are Indian people are generally using the tungsten hairpin, but is the foreign people are using the field emission. So field emission is the very costly, as well as the, but you can get the deeper and deeper, very clear information. This is your source size as well as the okay, no need to describe here. Okay. Another important thing, aperture. Aperture is also very important things that we can, with the help of this aperture, you can you can create the, you can create some problem. We can create some, we can tune your path of your electron beam. And also we can change the path of your electron beam, and that will, but basically, and how much energy is required for imaging process. So that will be very important. Also, we can reduce the noise and many more things with the help of only this aperture, and that will be give the different angle of for the electron beams. So that is also important parameter. So for the tilting of the electron beam and many more things, that will be the same as like your system will be looks like the blur images, and with the better images, and depth of you can also change with the help of only this with the aperture of your if you use the larger aperture, that will be depth of focus is lower. If you that aperture is smaller, that will be, you can find the depth of focus is very higher. So, and also that will be also that we can take the your resolution of the system in, as I told you, that we can take the in the pixel form and different squares, and that squares that will be collect the number of electron, how much number of electron that will be generated by your different area. So that will be looks like 100 micrometer, and that will be 100x, 10,000x, and that will be that with the help then we can find out the that is the scale that we completely, with the help of that scale, we can how much area that will be covered by the your electron beam as well as the your system. So that is also the pixel limitation is the but this is behind the one resolution, and how much resolution that your system can how much resolve. Generally that will be 100x to 1000 times of x is the SEM, but in the TM that is the more than 1 lakhs x is that can be resolve your system, that we can find out the your image as the your angstrom level, that is the atomic scale level in a TM, but in the SEM only is the nano region. And there is the this is a as I told you, there are two types of detector: back scatter detector. This is also called a solid state detector, and this is the secondary electron detector. And here that will be totally. So both are that is situated in the different places in a SEM in a column. So both detector cost is different. Both is the collect the number of electron is the collect energy is the different. So due to that, we are using the for a different imaging processes and for different types of detector. But so at different times, we cannot choose the same detector as the first. If you take the some better image is the better topography image, so we can take the back detector, and if you gain the topography, that will be use the secondary electron detector. So and also and the detector is the for the EDX. So with the help of, so there are three types of detector is the in the situated in the this SCM, back scatter, secondary, as well as for the EDS. And why do we need the vacuum in the whole system? Basically, that is the use that for the thermal stability, and also basically that we are using the very field emission gun. So for field emission gun, we need a very high vacuum. That is the vacuum at 10 power minus 10 torr. That this 10 torr is the very high. Without high quality turbo pump, we cannot achieve this level of vacuum. So due to that, your system cost is going to higher and higher. Only the quality of vacuum and many more things. Okay. That is another types of detector is the secondary environmental SEM. This is the environmental SEM. SEM is the this is for the different process and different process, and this is we need the different pressure and different gases, and this is different press different things about this. 1 minute, sorry, somebody is in my office. He need my help. So why SEM? Basically, environmental SEM. This is basically if you have the biological sample, this is the biological sample is very vacuum sensitive. Basically, sometimes we are using living and non-living sample. This is very easily that will be that will sample will be radiate, and that will be, and this that will be and also this is oily and basically and dirty and some greasy sample. So we need this environmental SEM for getting the better and better image. And a normal SEM we cannot collect the information in the biological sample as well as the any organic sample. So for the organic sample and biological sample, we need the environmental SEM. Basically, this environmental SEM work as very low pressure, low that is require very low vacuum system. So that is also we can basically mechanical stress testing, oxidation of metal, and any hydration and dehydration. Then we can choose the with the help of this environmental SEM, we can find out more and more image. And that will be, and that was his basic difference between SCM and TM. In a SCM, that is that high resolution for the bulk sample, but in TM, that is we need the very thin sample, and resolution of this nearly nano region And but is the in a TM we can find out the some 1.2 to 1.5 Angstrom level. Most commercial instrument is available. And most important thing in SEM, we can find out the 3D image of the specimen, and that in a large area and large data focus. But in a TM that we cannot find the very 3D image. And SEM is a completely very low cost, and that also we can collect we can find out the very low magnification. And but in TM is the very very costly. I think if you think about the cost, then SEM is nearly 2 crore and TM is right now more than 15 crore. So also, but we can complete information we can collect from the only TM is the structural information and orientation and dislocation, any tuning of the simple as the nano level. So if you want to give the complete growth mechanism and many more things, so for this we need the TM. Summary of my talk is the basically I have described only mainly of this secondary electron microscopy, that is for the topography, and backscatter is that we use the chemistry purposes. Chemistry purposes is mainly is the ADX. Chemical chemistry is this is a chemical composition that will be used with the help of ADX. And also some I have not described about the ADX. Obviously time is not allowed. So, okay. So thank you very much. If you any query and any more things, so I want to give your answer. And
Thank you so much, sir, for such an insightful lecture. Meanwhile, sir, one of the question I will like you to address, because most of the time when researcher goes for the synthesis of any sample, so he is not very much clear which characterization technique he should use. As a fashion, firstly he goes for the XRD, then SEM, and then TEM. So can you throw some light when a scholar should go for SEM analysis, when he should go for TEM analysis? That is always
okay, yeah, 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 yeah. Very good question for the young researcher.
yes.
If you prepare some sample, first you go for the XRD. Without X-ray diffraction, that X-ray diffraction give the gross is the very big amount gross structure of the gross information of your materials. Okay. After that, you move your structural as though you can move for the property. If you give your sample is very good property, then you move for the SCM as well as the TM. Otherwise, no meaning. So first you prepare your sample. If you want to dope as well as I think you want to prepare pure sample, any types of sample you want to prepare. First you move for the your XRD, X-ray diffraction, and then you can find with the help of JCPDS card many more information. If you go for the more and more detail information, you can move for the readable refinement. I think today I think
Yes.
Dr. Anwar will be discussed about the readable refinement. Then he will give the brief about this. So, so then after that you can move for the if you work on the your growth. I think some you can prepare your new sample. So move for the scanning electron microscopy and transmission microscopy. If otherwise that material is old and nothing is new, so first you move for the your property measurement as like the optical and electrical and dielectric, any types of property you want to measure. So after that, if everything is good, then you can move for the detailed structural if basically if I think if you prepare the sample by that is completely depend on the methods, which type of method you would choose, the physical methods, chemical methods, which type of method you can use for the preparing your samples. That is the totally depend upon your also internal structure of the materials. So finally you can move the transmission electron microscopy, then you can conclude and then you can give some science behind the your property and application, any more things.
Thank you so much, sir. I think the scholars may have been benefited by this answer. Any other?
Yeah, yeah.
So I think, sir, there is no question. Sir, how to know? Acha. Sir, there is one question. Shelja Saxena wants to ask, how to know which area of sample should capture for same image?
Same. Yeah, that is also very good. Uh, basically, when you prepare your sample, generally people are using a pellet. Sometimes people are using the people a powder sample. If you use your powder sample, that is your scan the whole area behind the. Basically, if you work on the nano region, then that is very one of the tedious and tough job to control growth. I think sometimes if you use the physical science techniques, that will be not uniform structure you can get. So that basically in a chemical method that you can get the some more uniform structures, inform I think material will be grow, and that image that you can find that there is no blur image observe, and also you can first you if your material will be insulator or mini more, first you coat it with the gold and silver. After that you can move for the imaging process, and you can choose the better and better and good quality. There is no impurity and there is no some random structure that is no observed. Then you can collect your image, and that after then you can take for publication purpose anymore, your thesis purpose.
Thank you, sir. One more question is there. Will sample preparation be modified to get clear individual structures? When I analyzed powder sample, it looked sewed together. However, it had distinct structures. So may I request Shelja, you can unmute yourself. No, this is Neetu. Neetu, I am going to unmute you, or you can unmute yourself and you can ask your question directly. Because I hope it is not a single question. It is group of question is there. Neetu,
Okay, no problem.
that is first is will sample preparation be modified to get clear individual structure?
Sorry.
Sir, let me unmute this
Hello.
participant.
Am
Yes.
I audible?
Yeah.
Yes,
Sir?
yes.
Yes. Okay. Hi, sir. Very informative session. But I have a
Okay.
question. Like when I analyzed my sample through SEM, it was a powder sample.
Which
So
which sample?
however,
Which sample?
it was chromium
Material
nanoparticles, sir.
name. Sorry, gold nanoparticle.
Chromium oxide nanoparticles.
Okay. Chromium oxide. Okay. Please.
Chromium oxide nanoparticle. So
Okay.
when I analyzed it, it had a sort of hexagonal structure, but I felt like, when we analyze large amount of powder, how it will look like a sort of togetherness I felt. Okay. So I would like the sample preparations can be modified or any like since I saw the presentation samples that distant samples could be seen. I would like to know if any such sample preparation techniques are there for SEM.
Nothing. Sample preparation is only required in the for biological sample. For your sample, there is no special type of sample preparation. That is very simple things. I think this is beauty of SCM. For a solid sample or this is some oxide sample, there is no special preparation is required. For a biological sample, we need the very complicated and simple preparation is required. So for only
Okay, sir.
if you not get very good images and anything, then you can only you can coat your sample only by gold and silver, that you can get the very good image, and that your image will be not basically chromium is the basically magnetic material. So due to that
Yes.
magnetic material will be charged. Sometimes your material will be just charged with the electron beams. So you cannot get this very clear and very good image if your I think that people are not expert, so you cannot collect very good image, especially on chromium
Okay.
and iron many more this type of
Okay.
materials.
Okay, sir. Thank you so much, sir. Thank you, sir. Yes.
Okay.
Thank you, sir. Any other questions, participants? Sir, I think there is no question now. So,
Okay, ma'am.
sir, meanwhile, I will ask one question again for the benefit of
Okay.
participants.
You can ask anytime, madam. You can
Yeah,
ask anytime.
so
Okay.
asking in this particular platform may benefit others also. So the
Okay, okay, sure.
simple is kindly let students or participants know where to get SEM and TEM from easily.
I think right now India is in the many institute. I think AIMS Delhi is a good, there are several other places is very freely available in a nuclear center Delhi, and also DAE center in the Indore. Basically, that is at both places are freely available. But in many places that there's the huge charges. MBHU, I think more than 10 TM and SEM is available, but cost is very high, nearly 1,000 per sample or per hours. So, and I think in Goa, BITS Goa, somebody yesterday told me BITS Goa, and also in Sagar University, many universities that is available, but is a totally depend upon cost and many more things. Especially in a TM, that is basically in a that system is maximum time is a breakdown due to several reasons. So that is, but in a SEM, that is, I think there is no problem. People can search and go behind IIT, BHU and BHU and Sagar Institute and AIMS Delhi, IIT Delhi and NIT Delhi. Many more nearby. I think many instrument is available for this purposes.
Okay. Thank you so much, sir. Over to
And
Madhu.
JNU is also a good research center for this purposes for outsider. Okay.
Thank you, sir, for this information. Over to Madhvi Dhingra, ma'am. Madhvi, ma'am.
Yes, sir. Uh, a very we are very thankful to sir for giving his precious time, and thank you, sir, for giving your time over here. And we would like to have future collaborations with you as well. Thank you, sir.
Thank you, ma'am. Thank
Thank you
you.
very much, sir. Thank you.
Thank you, sir. Thank you.
Thank you, sir. And sir is also a mentor, or you can say instrumental in
Oh,
planning this particular workshop. So special thanks.
okay,
to
okay,
sir.
sure.
Thank you.
Chali.
Thank you, sir.
Okay,
Thank you.
physically this is better. I think I think in a online many things I cannot explain more and more detail. So
Yeah,
that is
yeah, that is.
one of the problem, one of the biggest
Yeah,
problem.
sir,
Okay, no issue.
Okay, sir.
Thank you, sir.
Thank you, ma'am.
Thank you,
Thank
sir,
you.
for coming. Thank you.
Okay, bye.
Thank you.
A very good afternoon to all the ladies and gentlemen who are present here. Today we are on the session 6 of National Workshop on Advanced Synthesis and Characterization Techniques. So today we are honored to have with us Dr. Mohammad Shahid Anwar, who is working as Senior Principal Scientist from CSIR Bhubaneswar. Before calling him on the dais to speak, I would like to give his brief introduction. Dr. Mohammad Shahid Anwar has joined Council service in CSIR CECRI as scientist during Feb 2008 and worked there till March 2011. Upon transfer, he joined CSIR IMMT in April 2011 as scientist. Currently, he has been undertaking research independently in interdisciplinary areas. His work is mainly focused on development of coating and energy materials, especially on thermoelectric and proton conducting SOFC. An alumnus of UGC DAE Consortium for Scientific Research, Indore, where he joined as JRF under DST project and later on for PhD in Dr. N.P. Lala Group. Prior to PhD, he also completed his education from St. Aloysius College, RDVV, Jabalpur, for bachelor degree in electronics and master's MSc in physics in 2001. He was awarded PhD degree on the thesis entitled Structural and Dielectrics Studies on some perovskites-based oxide from DAVV Indore. He bagged Young Scientist Award by MP government for his doctoral work. Currently, Dr. Anwar is involved and also leading various projects funded by CSIR, DAE, BRNS, SERV, and other reputed agencies with focus on development of mechanical coating and energy materials. His area of interest include electron microscopy, ferroelectrics, multiferroic, fuel cell, thermoelectric materials, metallic thin films, etc. He is also guiding various students for PhD, MTech, and MSc dissertation and short-term training. Dr. Anwar has published over 100 SCI journal papers in multidisciplinary areas. He is also a member to various professional societies and actively engaged as reviewer to many journals of international repute. He has also experience of senior scientist from IMMT Bhubaneswar, then Zurich University, Medgyung, Germany, and collides in mechanical material chemistry department that is from Tamil Nadu also. If I talk about his awards, then he has received Bhaskara Advanced Solar Energy Fellowship Award in 2019 by DST India, Madhya Pradesh Young Scientist Award for Physics in 2009 by MPCST, National Scholarship DST, JRF and SRF Award during this 2002 and 2006, and also received National Scholarship CSIR SRF Award in 2008. So with this, I would like to invite you, sir, for your session on grid field analysis. Please, sir.
Thank you, madam. Thank you for elaborate introductions. Okay. So I think my screen is visible.
Yes, sir, it's visible.
Okay, so I think we can start directly. I think all participants are here.
Yes, sir, you can start.
Okay, so good afternoon to all the participants, all the organizing committee. So today I'll be talking about retrieval refinement of powder X-ray data. So as madam told, I'll just briefly introduce about myself. I'm Dr. Mohammad Shahid Anwar, a senior principal scientist from Material Chemistry Department of CSIR Institute and Institute of Minerals and Materials Technology. So before start my work, I'll acknowledge the organizer of this 1 week national workshop on advanced synthesis and characterization technique, and also wants to acknowledge MIT School of Engineering Technology for giving me an opportunity to present some of my work in front of you all. And also Dr. Manisha, who is consistently in touch with me and requesting for me to give a brief presentation on ritual refinement. Okay, so before starting the official lecture, I just introduced about my institute or my parent organization. So I belongs to CSIR, CSIR. Okay, so I think most of you are well aware about CSIR, the full form of which is Council for Scientific and Industrial Research of India. So we are having an organization which is started before independence. So we pre-independence institute in which I am working, and this was registered by a society act. So the CSIR president is Prime Minister of our country, and the vice president is the Minister of Science and Technology of this society, and DGCSIR is the secretary of this institute, this society. Okay, so we have 37 research laboratory across all the tick and corner of the country, denting all the area of sciences. Science, engineering science, chemical science, biological science, physical science, all. So whatever you can think of, we are working. Some of our lab is working on that area. So apart from that, most of you are PhD scholars are well aware about the CSIR fellowship. So CSIR provides thousands of fellowship every year for PhDs. Okay, and we have a lot of achievement to show. CSIR means, as I told you, we are working in all the tick and corner of country as well as all the tick and corner of the R&D. whether you are talking about air, space, our presence is there, whether it is deep sea level, our presence is there, or in the area of mineral, material, aerospace, mechanical engineering, whatever you can think of, our presence is there, and we are leading research in the country. Okay, and since it's a government organization, so we are working mainly for public sector. Okay, so this is my institute, the CSIR, Institute of Minerals and Material Technology from Bhubaneswar. We work mainly on minerals and materials. I work on material chemistry department. We work mainly on coatings, energy material devices, batteries, supercapacitors, thermoelectrics, piezoelectric, whatever you can think of any aspect of chemistry, we are working on that. And we are mainly working on different projects funded by different organizations. Not only we, material chemistry department, but advanced material technology department is there. There we work on mainly on plasma techniques, some metallurgical aspect, pyrometallurgy, all kind of things, coatings, thin film, hard coatings, soft coatings, all things they are working. Central characterization department is equipped with lot of facilities. Similarly, mineral processing department for mineral aspect, hydroelectrometallurgy for hydrometallurgy, environment sustainability department to look after the environment impact on this from these activities. Apart from that, we are having a design and project engineering department, which mainly work on societal impact, which is related to local public only. So what are issues related to that, just like filter water, chulas, all those things, we work on that. Okay. Process modeling department, computer networking department are there to support our activities, our means all in departmental activities on that. For PhD scholars, these are the research activities. What I told you, we are working on that. So any research activities you people want to undergo, or you want to are interested, or you want to use it, you can come see, visit, or if you are a PhD scholar or if you want to do PhD, you can come in contact with us, and we are having a lot of things to offer you. Apart from R&Ds, we are having good facilities of all-round development, whether it is a canteen, hostel, ground, indoor, outdoor, everything we are having, and we are located in the heart of the city. Okay. So since this lecture I am giving at Gwalior, so I just placed few laboratories in and around Gwalior, Bhopal, Nagpur, Delhi, Lucknow, CBRA. We are having all kind of laboratory, and each laboratory is specialized in some or other activities of you. So this is just for your information and for your future aspect. Where if you want to use it, if you want to join it, you can come, have a look, join it, and if you're interested, then join it. Else you are working there. Okay. So we'll be talking about ritual. While coming to the subject of ritual refinement, the main aspect of this or why we need a ritual refinement. We are already having X-ray, XRD. We are working with that. Then why we need X-ray diffraction? Okay. So before, I think you people have already understood about X-ray diffraction. I'll just brief it out about X-ray diffraction, whether it is really important or not. Okay. So X-ray diffraction is one of the, you can say, landmark experiments. X-ray was one of the landmark discovery in the history of science or in the history of material science. Whatever book somebody has compiled, whether it's 10 landmark 5 landmark experiments, 20 landmark experiment, or 100 landmark experiment, you will find X-ray in among those things. So without the I think this can be suppressed. Okay. Okay, without the place of X-rays, the wave nature of X-rays, this list cannot be completed. So you can realize that how powerful this discovery was, and the wave nature of X-rays. Okay, so for X-rays, X-ray has come into the picture in the 70s or late 70s or early 80s, where really it has been started. But it's not like that before that structure was not available, or before that symmetries was not known. Earlier also, people were using gemstones, or where the snowflakes are coming. Means, so those things are still existing before that era. Okay. So what people have thought of. So those, whatever the heavenly bodies objects are there, they are also having some kind of regular arrangement, regular symmetries. Earlier, all the philosopher experimentals were very limited, but earlier philosopher was there, or those who were thinking, seeing, visualizing, and just they are writing without doing experiment. They are understanding. So initially, they have thought that there might be some regular space, some regular shape which has been arranged in some pattern. That's why these shapes are arranged so regularly. Okay. Earlier, there was no only regular shape was they have shown some building blocks. There was no concept of unit cell. There was no concept of crystal structure. There was no concept of electron, proton. And later on, things had come, but they started with the idea of regular shapes. The earlier experiment, you can say scientists who were worked with those things were Kepler and Hooke's. So Kepler, you might have heard with Kepler law, who have studied heavenly bodies like motion of Earth and other things. They similarly Hooke's law and spring constant, other thing. But no, they are the father. Actually, they are the father of the crystallographers. Where initially work, they have started with the crystallography of these things. Thus, they started guessing the things. Okay, kind of arrangement, regular arrangement. In modern physics, we call it an atoms, but earlier they were saying some regular arrangement or some building blocks. Okay. So how powerful the discovery of X-ray was that in 1901, first Nobel Prize was given to Röntgen, who discovered X-rays. Okay. So initially it was used for medical purpose. Nothing was known, so that's why its name is called X-rays. Later on, von Lau has used that X-ray. Since before that, optical light has been established, gratings experiment has been established, optical microscope has been established. So some of the theories has been established. So similar to that of concept, von Lau has proposed some concept of diffraction of crystal because of the wavelength what they have used, what they've generated for X-rays, and the size of the crystal. He thought if the size matches with the crystal and if X-rays have wave nature, then it will give diffraction. So that was proposed by von Lau, and it was experimental proof which gave him the law, which gave him the Nobel Prize. But Bragg's was the genius, their father-son pair, who really used those X-rays and the concept of von Lau and finally implemented on crystals. And they started doing experimental on the basis of that theory and establishing the crystal structure arrangement regularly. Okay, they have used the position and space lattice arrangement, space lattice and atomic arrangement to solve the crystal structure. So this shows how strong that was. So what was the von Lau postulate? The first thing he said, if crystals are periodic arrangement and X-rays are wave, then this crystal can act as a 3D diffraction grating for X-rays. So here he has taken two if. If any of the if is failed, then this theory won't exist. It won't give a actual result for that one. So first if was crystal are periodically arrangement of atoms, and second if was X-rays are wave. These two things was not established earlier. So with this experiment only, so he said, okay, if they are crystal arrangement and if X-rays are wave, then it will give diffraction. How will verify diffraction? This is the first diffraction experiment he has placed, and what he has shown, if there is no diffraction, it will give a center spot without any deviation of the beam or X-rays. Okay, if there is a diffraction, then apart from center, you will get some kind of spots. You get some kind of spot other than the center beam. So with this experiment, with this observation, he proved these two if, and he got a diffracted beam. This was the with later utilization, and these two experiment was proof. Okay, so X-ray diffraction says peak position and peak intensity. I'll just go a little bit fast because I think you people have already studied. I'll just cover this thing, what is really related to our topic. So X-ray say crystal structure, lattice motif. So what is X-ray diffraction? A beam is incidentally on some sample, it transmitted, then it's got some diffraction beam you will get other than the direction of the transmitted beam. So in which direction? It will give diffraction in all the direction, not in a one particular direction, because diffracted beam will come to all the direction. So this was just example. If you say there is a crystal lattice, if the X-ray beam is coming, then it will diffract in all the direction. So this was the case of one atom. Then similarly, if beam is coming, falling, a parallel beam is coming and falling to all the atoms, then it will get diffraction. Let's say I'll take a particular direction, or let's say this direction. So if all the beam construct interferably, then you will get an intense beam of that direction. Okay. So what Bragg said, yes, if you want what if a beam is coming to the particular direction, then it at a certain direction where phase angle things matches, and you will get a convergent, or you will get a superimposition on of the beam. Then you will get, I can convert the diffraction by considering an imaging plane, and this will convert to a reflection. Why he want to convert it a reflection? Because reflection thing was already established, and with this he got a lot of simplicity in the experimental analysis. Okay, so this was the original Bragg's law. What Bragg's law is saying, so if you'll give me another direction, I will give you another certain set of planes in which you will be able to satisfy the reflection condition by another imaginary plane tilted in another direction. So Bragg's law says for every diffracted beam, there exists a set of crystal lattice plane such that diffractor beam appear to be spectrally reflected from this set of planes. Whatever beam you will take, he can say, I can give you a spectrally reflected set of planes in which it appears to be a reflected beam rather than a diffracted beam. So this is the original Bragg's law. Everywhere we are talking about 2D sine theta, that is the only a mathematical representation of Bragg's law. But original Bragg's law was the earlier what he said. Okay. So these are the formulas what we can with the help of this plain mathematical relation. All these are mathematics only. So I will not go into detail of this one. So we will have a X-ray diffraction. So depending upon the material what we are having, we will get different type of diffraction. Earlier we used to get a ring pattern, because with the advancement of science, technology, detector and these things, nowadays graphs directly with the detector. Earlier we used to do with this of photographic films. Depending upon the ingredients, you will get different type of patterns. The first thing you can do. So in an X-ray diffraction pattern, what we will get? This is very important. You should understand, you should write those things also. If in any diffraction pattern, we have two things. The first thing is background, and another thing is reflection. So in reflection, what is there? We have a reflection intensity. And what we have? Reflection profile. Anything else we can get from reflection? Yes, I can get information like position of the reflection. These are the three things we can get from reflection. And each thing is responsible for giving information about the following thing. From intensity, we can gather information about crystal structure. We can gather information about atomic positions, temperature factor, occupancy, phase analysis, quantification, we can do it. From the reflection profile, peak profile, we can get particle size as well as strain information. What type of profile? Then accordingly, these information are present in that. Similarly, if I talk about position, different, because you might have seen X-ray diffraction and every time positions are shifting. So why it is shifting? Because they are having different type of or different dimension of unit cell parameters. They have different symmetries. They have different crystals are having different space group. So these thing information we can get it from positions. Okay. Then we can also do phase analysis qualitative wise. Okay. Apart from reflection, we have backgrounds. So background, what background will give information? It will give information about sample, Compton spectrum, TDS, thermal diffusive scan, amorphous content, local disorders, all those thing information we will get. So in a ritual refinement pattern, we will provide him a X-ray diffraction. So X-ray diffraction can give these kind of information. So these are the possible things which we can gather. Okay, although we are not taking all the information because some other supportive information we have to put, but theoretically, ideally, we can get all these information with this while refining from the X-ray diffraction data. So how we use X-ray diffraction data in real-time problems normally? If you any of or if some research scholars are there, so I'll just ask to them, okay, how you used the most of the thing. Mostly what people used to do, first thing is they used to see the image, okay, what kind of diffraction having, whether it is a sharp peak or whether it is a broad peak or whether it is a little bit hump kind of thing is there. So if it is a very sharp peak, then they can say, okay, I am having a single crystal. If I have very sharp peak and very limited number of peak of same time, then I can say I am having single crystal. If there is a little bit width is there and lot of peaks are present, then I can say, okay, crystalline is there, but it's a polycrystalline material. Then if I have a amorphous kind of thing, a peak like this, then I can say I'm having an amorphous. If it is a monoatomic gas, I'll get diffraction pattern like this, where intensity is continuously decreasing. So first thing is visual inspection we can do with X-ray, and I can say whether my material is amorphous, crystalline, or an monoatomic gas. Okay. The most common analysis method, what people used to do after taking X-ray diffraction, what they do? They take JCPDS data, compare the JCPDS data, assign the peaks with respect to JCPDS data, and they used to report. This is, I can say, this is just a beginning. This is just a first information they can get, not the exact and final information. Okay. While using JCPDS data, also you have to be very careful with lot other things. First thing is you have to look for the quality, what kind of quality he is having, whether it is a C, whether it's a star quality, whether it's a deleted. If it is a deleted, that means data is wrong. Earlier the data was provided, later it was proven wrong, so they have deleted. Since some number has been assigned, so they keep the data, but they write it deleted. So first thing you have to check what kind of quality you are having deleted. The second thing, don't directly focus on the peak position. Apart from peak position, see peak intensities also. Because if material is same, then intensity profile or intensity, you can say ratio will also match with that of the pattern. Okay. So this thing we have to be very careful while comparing. Okay. So most of the people use like this, and they report in the paper or they report in the data. Okay, I'm using this and I will match with this, and this my phase with this structure with this lattice parameter. Okay, you got the first information with JCPDS data. What else you can do from that X-ray data? Okay. Earlier, what people used to do, they used to do some kind of calculations, and with the help of calculation, they do with the help of calculation with the established parameters, they determine the lattice parameters and the structure of the cell. So this is one of the module what I can say, a research scholar can always follow initial module like this, and based on that they can find what kind of structure or what kind of lattice pattern material having. So these are the well-established mathematical formulas. Any of the basics crystallography book, you will get these information available. If my structure is primitive, cubic primitive, then I'll have all kind of reflection. If it is a body center, then all even reflections are present. If I am having a face center, then this say in general I can say primitive all, body center if their sum is even, face center if it is an unmixed. Okay. So if I use this mathematical formula and this established theory, and I have an X-ray diffraction pattern, so I can calculate what kind of pattern it is having. So 2 theta value I can know. I can know the peak number 1, 2, 3. I assign the peak 2 theta value. Accordingly, if I'll find sine squared theta of this 2 theta value, then I have having some value. then then I can determine what is the minimum of that, and then I'll take a ratio of that one. So sine square theta by sine square theta minimum, here minimum is 0.188. So with this, I can have this number, and I can see with this, yeah, there is some number. If I'll multiply, then everything will become a regular, or you can say a round numbering. So here, if I'll multiply by 3, most of the number will become, either they will become or they will become very close to that of a round figure. So 3, 3.999, 7.99, 10.99. So I'll make a round figure, and that can be assigned to h square plus k square plus l square. And if I know the h square, k square this, then I can find the HKL value with this number. And with this, I can find, using the formulas, using this formulas, I can find the value of A. So this is my A, and from everything, I'll get the value of A. Similarly, another method is there in which I can again determine this by, instead of taking sine square theta by sine square minimum, I can take sine square theta by 2, sine square theta by 3, sine square theta by 4. And from here, I can take 6, 7, 8, 9, whatever you feel, you can take it. And from there, I'll find a number. I can find a number which is very much common in all those things, most of the things. So here I can find 0.03 is coming very repeatedly in most of the lines. So that is the number I can divide by this number, lambda by 2a, that is the number, this is the ratio. And from there, I can find the value of A. Okay. And similarly, using those pattern, I can find h square plus k square plus L, and I can decide. These are some example. If you want, I can give it to you for calculations. Okay. Another thing we used to do with X-ray data is the particle size analysis using Scherrer formula. I think most of you used to do, but this is not the correct way. Okay. Although this is very much in use by various researchers, but this is not the accurate method. Okay, this is applicable under certain conditions. Okay, so I'll just tell you, okay, if I can use this value, and I am putting the lambda and half full width at half maxima, I can put the value of this thing, and I can find the value. But as I told you, this is not the accurate, because crystal structure is not always the accurate number or accurate crystals with strain free and other things. Okay, so we have crystal lattice. The peak profile definitely tell about the crystallite size, but simultaneously it has some amount of strain also. So if some kind of strain is there because of insertion of some inhomogeneity or impurity, or some kind of compression or suppression, so you will have, instead of getting with parallel beam incidence, you should get parallel beam of diffraction or reflection. But here, because of this kind of strain in the system, your peak varies. So instead of getting position here, you will get a shifted position, or you will get a broad position. So these things will also affect your profile. Okay. So ideally, this A, what I'm saying, center beam is the material contribution of your crystallite side. But if there is some kind of instrument effect, then this peak, ideally, which has to be a straight line, will become this much broad peak. Okay. If along with some kind of instrument, there is some crystallite size, other thing is there, combined effect, then it will become like this. If any strain is there, then combined effect of strain will also come like this. So ideally, you should have a peak like this, but you are getting peak like this. So here, if this kind of situation arises, then instead of you can misinterpret your material information with respect to single crystalline to a polycrystalline. The most accurate method is given by Williamson-Hall method, in which he has considered not only strain size, but he considered the strain things also. And with this kind of mathematical representation, addition, subtraction, you can find this equation can be fitted in the form of straight line, and the intercept will give you the strain, and the slope will give you the particle size of the system. Okay. So these are the very general thing what we can get manually from this X-ray diffraction data. Now, advanced analysis. What was our main topic? How people use advanced analysis with this. If you start doing the way what I have told you earlier people were doing like that, but it takes time, huge amount of time. with the advancement of technology, with the introduction of computers, high-speeding computers, this has made our life easy. Okay, so ritual refinement is one of the things in which we take a raw data, we refine the data, and we extract the information, what I told you earlier, from the peak positions, peak profile, peak intensity, and the background. Those information can be easily taken it out from ritual refinement. Okay, so this is the raw data, what we usually observe, and this is the refined thing in which we can extract information. This I'll tell you later on, but this is just a way. So what information usually we take from a refined pattern? Normally we take what kind of structure symmetry it is having, what is the accurate lattice constant, what is the accurate bond angles. I am just giving an extra effort on accurate, because here accuracy will come into the picture. A small deviation also you can very easily locate it out. Okay. So why we want this kind of accurate information, whether it is really necessary or with the way what we are getting earlier, we can take it out and we can work it out. So with this accurate information, we can relate with the material properties of the ingredient, what kind of behavior that material is having. Okay. Most of the properties, material related properties, are rely on the above information. Before any theory or any concept or any support if you want to give, you need those information very accurately. Okay. So how we can do this kind of ritual refinement? So there are various paid, non-paid, freely available systems are available in different platforms where you can download those kind of softwares and you can do refinements. So foolproof, GSAS, written, there are few different software as per your convenience, as per your understanding. You can use any of those things. The basic concept by any of the software is same, what was proposed by R.A. Young in 1950s, 60s, and they made their different logical programs in different ways, and those are there. So this is one of the X-ray diffraction pattern. As I told you, peak shapes will give you particle size, accuracy, and the relative peak intensity will give you the atomic distribution. Diffuse scattering will give you about the sample holders, scatterings, matrix, what kind of matrix we are having, that is crystalline, amorphous, whatever things are there, you will get those kind of information from that peak positions other than that. Okay. So what is ritual refinement? Ritual refinement is a technique which was developed by Pogo Ritual. Okay. Based on a paper given by R.A. Young in the year 1950s. Okay. And what it do, it used, where it is used for characterization of a crystalline material. Characterization means, is it necessary for X-ray? No. It can use X-ray diffraction data, it can use neutron diffraction data of a powder single crystalline, then it generates the characteristic reflections, and then it do overlapping, or you can say fitting over that. So ritual refinement, what is the program it's having? It is a least square fitting approach. Okay, so it takes the data what you observe from any experiments, then with some information what you provide, it will prepare a model out of that one and then start matching. And with the concept of least square fitting, it do the fitting so that the data what you have been given, what the X-ray data you have given, that was the experimental one. What information we are given is the approximate. So it matches with, it generate data with your information and try to fit with your observations, X-ray data. And once it will fit by varying different quantities, once it will fit, then you will get the accurate information. So the paper was, ritual refinement was based on paper which was given by R.A. Young, as I told you, in 1950s, but the ritual refinement method was developed in 1967. Okay, So based on that, the first information or first thing reported in the year 1969. So earlier you can see when there was no computer, when there was no calculation thing, everything has to do manually. It took months to solve any kind of structures. Okay. So as I told you earlier, ritual refinement is a least square profile fitting approach. Okay. So what ritual refinement do? Ritual refinement method refined what it refines the user selected parameter. Some parameters you will give before starting, and it will minimize the difference between the experimental data and the model or the hypothesis of the crystal structure what you have provided with the instrumental parameters. Okay. So you have to provide some kind of input. What what information we can get from the refinement? Okay. So can in the information about single crystal, yes, it can refine. It can refine lattice parameter, it can refine atomic position, it can refine fractional occupancy or the thermal parameter, because whatever information you will give an approximate one. You cannot give any exact one. Okay, most of the time we don't have to, we used to give some based some literature, based on some paper, we'll used to give some approximate data or information. By the use of that approximate information, it refines and give you the accurate one. It will give you the information about the preferred orientation, what your sample is having, especially in the case of oriented samples or single crystalline sample. And if you're having different kind of phases, then it will give the information of all those phases also separately, so that you can identify what I am having a single phase or biphase or triphase or multi-phase samples. Okay. So as I told you earlier, virtual refinement method is for refinement of the crystal structure. So what does it mean? It means you should have a crystal structure with some atomic positions. It will, after refinement, it will give the crystal positions very precisely. So before that, you have to give some kind of information. For example, I'm having a lanthanum cobalt crystals, lanthanum cobalt aluminate crystals. Then I should be aware about what kind of space group it is having, what kind of approximate lattice parameter is having, and what kind of site occupancy is having, where my atoms used to go and sits. Okay. So this kind of information from where we can get? Either you can get from some previous papers, some most of the time what we do, we take some model, we take some, let's say, lanthanum cobalt aluminate, and we try to dope on the system. So if it is a very minor doping, then it will try to follow the lanthanum cobalt parent matrix. If it is away, then it will try to break the thing. So those information we can get it from the literature. And with that, uh, with this, I can, in general, I can talk about reflection position and reflection intensity. So from where I'll get this information? Okay. Here it's not written. Okay, I'll just tell you earlier or later on. What we want from ritual refinement before doing any kind of experiments, before doing any kind of refinement or fitting, I need a good quality data. The first and foremost requirement is a good quality data. If you don't have a good quality data, then you will end up in some kind of confusion. You will not get a good refined pattern. Okay. Then I should, if I'm having a good data, then I should prepare a model. How I can prepare a model? I cannot prepare a model blindly. I have to prepare a model which have some physical and chemical senses. Okay, physical and chemical sense means which should be a logical one. Okay. Then I should have some kind of peak and background functions. Okay. So for obtaining a good quality data, what we can do, what we have to do, or what is in our hand, I should use a good system, a good high power system, plus not only a high power system, but that instrument should be aligned and calibrated properly so that it will not generate some kind of error by its own. Okay, there should not be any beam overflow problem, the sample errors. So these are the certain error which was coming due with instruments. Okay, so these are called instrumental errors. So these things we have to avoid. We should prepare a good quality samples with high packing, uniform particle size. There shouldn't be any orientation. If these things we can consider whatever in our hand, then we'll get a very good quality data. Okay, the first thing is high quality data. Then I need a structure model. The structure model means I should have what kind of unit cell I'm having, what kind of a space group I I should use, what kind of lattice parameter it should have, what kind of atomic position, atomic site occupancy. These are the few information which I should have in our hand before doing any kind of experiment. For example, let's say one of my material is lab 6, lanthanum hexaborate. So with this information that my space group is PM by 3M, and with lattice parameters is a cubic, so it's all ABC is the same, 4.15, let's say, and with atomic position, like just like what we say coordinates of a unit cell. Since coordinates of, if I say coordinates, then it's very much restricted to that unit cell. But if it is a generalized for any kind of unit cell, for any extension, I can tell it's a Wyckoff side. Okay, but and for understanding, both are same. So let's say my lanthanum is sitting at 0, 0, 0. X is equal to 0, Y is equal to 0, and Z is equal to 0 position. So coordinate is 0, 0, 0, but when we'll include the site occupancy, then it will become Wyckoff position, and I can tell it's a 1A. Similarly, 6F for this position, so that I can assign and I can generate a crystal structure of that one. So with this information, I can prepare a crystal structure, and in reverse, I can prepare a theoretically X-ray diffraction pattern of this crystal. Okay, so where I'll get this kind of information, my structure is, my space group is this, my material, let's parameter this, and my Wyckoff position this. So this information, I can get it from these websites, some database, some literature. Most of things are free, and nowadays a lot of new things are coming. Some are free, some are paid. Well, you can get this information easily from the literature. You can get it down. You can get those information quite easily. And once you gather all this information, you can start doing ritual refinements. Okay. So what is ritual refinement? So you have a crystal structure, you have a lattice parameter information, you have space group. So accordingly, what ritual refinement will do, it will, based on that structure, Wyckoff position, atomic positions, symmetries, it will, and the instrument error and data, it will prepare intensity pattern. What it is having, how it is using. So this is the formalism of this intensity calculation, in which it will consider the background. It is having a factor like scale factor, because each instrument is having different power, different kind of slit arrangement. So their output intensity will be different. So it is having what it will consider, not only background scale factor, but for Miller indices, which is representing crystal structure symmetry, some kind of corrections because of the instrumental error, the structural factors because of the atomic position, site occupancy. Similarly, profile also, it will take care to determine particle size, stress, strain, other things. So this final I intensity is the combination of most of the information which is either available or which we want to determine from the ritual refinement pattern. Okay. So whenever we'll come to refinement, these are the very common terminology you will come across in the refinements. So what kind, people will ask what kind of backgrounds you are having, what kind of peak profile you are having. Peak profile means that parameters are called UVW, which is nothing other than Caligoti parameters which define the peak shapes of the function. Okay, then pseudo-Wyckoff means your how much Gaussian and how much Lorentzian fact contribution is there in your profile. Then what kind of symmetric, asymmetric corrections, and isotope drawing, any instrumental error like zero shifting, sample displacement, absorption, excitation, roughness, porosity, things are also coming into the picture of your thing. So profile, as I told you, the UVW parameter is defined by this formula, and that is called Kalogati function. Okay, so these are not much information. Simultaneously, if we talk about geometry, so these are the things which a 2 theta, while providing 2 theta, this is not for you. Okay, this software will consider these informations. So software will take care of your axial divergence, sample curvature, your transparency shifting error, sample displacement, zero. So these are the things what software will provide you, or what software will consider while refinement your actual data with your model data. Okay. So while refining, how can I tell whether my refinement is good or bad? So those can be defined by RWP, that is called goodness of fit. How much goodness, or what is the minimum? The number is minimum, the better is the fitting. Okay. So before refinement, there is a refinement strategy. You should be aware about those things. Okay, my refinement fit, because it's a multivariable fit, structure, background, profile, everything you are modeling. So there is always a possibility of getting stuck in some false minima. We want to, for a goodness of it, it's a least square fitting pattern. So whatever error is coming, that is, we are making square, and that under root, looking at under root, so that we'll get a low number of goodness of it. So ultimately, we want to go for a very low value of that fitting. So when we are finding variable parameters at a time, so always there's a possibility then I will get stuck while searching for a minima. We will get stuck in some false minima. Okay, we have to be a little bit careful. So that's why what we do, we also, to avoid these things, we do refinement in a systematic way, one by one, step by step. We start refinement with one variables, two variables, then adding one, two at a time, so that it should not get stuck by different variation at the same time. So what is the refinement strategy we have to do before refinement? First, we refine scale factors. So this is the pattern you should write, or you should keep in our mind. These are the refine. If now I'll tell you, after a few slides, I will tell you how to refine. But this order I have to be take care. Okay, first, I have to define the scale parameter. As I told you in the previous slide, there are a lot of variables which you can do. So what are those variables? These are those variables. If I start fitting all, then it will go and stuck. So instead, a lot of users, based on their experiments, they have made a strategy. Okay, first refine this, then refine zero, linear background, lattice parameter, mode background, peak width, atomic positions. Then only you will get a good fit without any divergence and without any minimum stacking or false informations. Okay. So this is a good choice for a beginner. You can, what you can do, you can limit instead along with the numbers, or along with the, you can say, systematics, you can lock those values also. Okay, no, I don't want to refine at a very large scale. I want to limit between these values. So those are the things what you have in your hand. So for that, if you want to read or more information about that, then you have to take these kind of references. Okay. Simultaneously, you can go, you Google, YouTube, and you will get more information about these things. Okay. So now I'll tell you how I can do. These are the things what we have understood theoretically. What we have, what are the concept behind that. Okay. So I think from here, some strategies are there, software wise. But before that, I'll just see if anybody is having any question, I can on those in that section, then I'll be happy to answer. Otherwise, I will go ahead of it. Some chats are there, so I can audio missing.
Participants, you can ask questions if
If
any.
participant, yeah, if any questions are there, then I'll happy to answer. Otherwise, I'll go for that software how I can do refinement with the software. Any questions?
Um, I can see no questions in chat box, sir.
Okay, there's no question in the chat box.
Yeah,
So I think I can go ahead.
yes, sir, yes.
So now, till now, what we have understood, everything we have understood theoretically. What is there inside a software or a reticle refinement pattern? How that thing use, what are the strategies that can be used, or what are the formula theory there inside that program? What are the logic programs are using? Now, how I can use those strategy in the defined program to refine my data. Okay. So as I told you, there are various softwares where you can use. Okay, where you can use to refine. I use WinPlotter. Okay. So apart from that, there are various other software like GSAS and other things where, as per your convenience, you can use those softwares. Okay. So I have what I can do. I can do before refinement. I should have a X-ray diffraction data. I should know about the software, and I should have these information like space group, lattice parameter, Wyckoff position. Let's say, for example, barium titrate, a well-defined crystal structure, a perovskite system with its space group is PM3M, lattice parameter is 3.9, and Wyckoff position. I know what are the coordinates. So these are the Wyckoff positions. The barium is sitting on corner side of 000 positions, and this is 000 position. This is 000 position, that is called at coordinates. But with the implementation of occupancy, site occupancy, as well as multiplicity, you will get this atom in every corner. Okay. That's why this is called Wyckoff positions. Similarly, titanium will sit at the center, so its position of multiplicity will always be in the center. So this cube center. Okay. So here, this is the barium, and oxygen will at the face. This face or this phase once at the center. So we have 6 phases. So there are 6 oxygen atoms on the 6 phases. That's why it's called a Wyckoff position. Based on that, I can prepare a profile like this. I will tell you later on how to prepare a profile, but this profile will look like this, in which these are some codes, what kind of refinement you can do, what kind of job you are applying, what kind of phases you are having. Okay, so everything is having a meaning, 0, 1, 2, because this is a coding. So everything is having a meaning of that one. So if you see the manual of this WinPlotter, you will get different numbers, 0, 1, 2, 3, 4, 5, 6, depending upon the limits, and each one is having certain meaning. You cannot do any deviation on that one. If you know your sample well, if you know all these information, and if you know the refinement you have to do, what kind of refinement, so always you can find one unique number depending upon your information, and you can place those information here. Okay. There are some certain like AU2, which can do some automatic refinement. There is ANA, which is called analysis also. It will show it to you in each cycle. So these understanding these things is not difficult. Just you want to know what is the meaning of which value. 0, what does 0 represent? What does 1 represent? Accordingly, you can choose and you can fit. Okay. What is important is the Wyckoff positions, what you want to give, what is the lattice parameter A, B, C you are having. Okay. So these are the certain, as I told you, these are the certain things which you should be aware before doing any kind of refinement. So after refinement, you will get this kind of data. Okay. So for all those who really want to refine and they want to know more about foolproof, where you search in Google foolproof, you will come with this website, and from here you can download the latest version. Every 6 months they are releasing the latest version, and you will get you will get lot of information. You will get lot of information along with the software from these websites. Okay, these are the, you can see some latest, old version, latest version, earlier version. Some everything is there in the websites. Okay. So once you install, you will get this kind of icon. FPS is written over there. This is called foolproof software. Okay. FPS means foolproof. Once you will click, you will open, you will get this kind of window. Okay. So for foolproof, if we are more interested on this window, just once you click this, you will open this software. Apart from this, you will have lot other software also depend upon, because this is our multi-purpose software with lot of information, lot of refinement, and lot of data analysis. So it's a general equipment, general software. So we'll have lot of options there, but we are more interested on this icon. Once we'll click this icon, we will get a WinPlotter software open in our screen. Okay. So now what are the few important places where we have to look for? The one, this which will tell you or which will open your data file. Then this is the edit PCR from where you can prepare your input file, what I told you earlier. Similarly, this PCR, while refinement, you can see your PCR, or after refinement, you can see before and after refinement, and do comparison of your refined data. Similarly, later on, if you want to plot, you can use this plot software. These are the few important things which we use very regularly, along with the others. Other things are little bit less used, but for refinement, these are the 4 things which we use regularly. So once you click open, then you can open your data also by selecting the what kind of profile your data, or what kind of profile your instrument will gives. Either the instrument will give this kind of data, or you have to convert in this pattern. This pattern is T initial, step, and T final. Just like this. Let's say I prepared a file like BT. Then here I can see, okay, TI means input starting 2 theta, then T, and then what is the step of each data, difference of the data, and then what is the final 2 theta value from where we have stopped the experimentation. Okay, so once you once you prepare your data like this, then directly you can upload with this software by clicking here and OK. So you can, once you click OK, selecting, then you will get a plot on that one. Okay, plot means same you can do in Origin also, but here seeing, visualizing, plotting, unplotting is very easy. That's why we used to do for first checkup only. Now I will come to preparing of an input file. That is the most important thing. If you want to refine any data, you have to prepare. You have to prepare an input file based on the information. What I told you earlier, you should be aware with your input data, space group, Y composition. So all this information you have to provide it here in the edit PCR column. So once you click this icon, you will get this window will open, and here you have to provide the information. So here, once you will open this, then you will see, you will observe that these all are inactive windows, because nothing, only window is open because there is no data input has been given to him. Okay, so here, once you will click here, then it will open a fresh file of your, and immediately it will become an active windows. Now start giving information about your samples, what you're having. Okay, so now will come the experimental module, real data. Okay, so this we have already discussed. I think this is the second part of the program. Okay, So this thing this thing is there. So with this, I can here you have to provide the information about your samples. If you go for general, you can provide general information, what kind of data you are having, where is your data location, then what kind of pattern you are having, how many phases, 1 phase, 2 phase, 3 phases you are having, what kind of background you want to give, three polynomial, 6-degree polynomial, 8-degree polynomial, what kind of refinement you want to do with the help of atomic positions, profiles, number of cycle, distance parameter, everything you can do. So we will run I'll just show you one real example of this one. Okay, we'll come back here again. So let's say, as I told you earlier, this screen is visible to everyone.
Yes, sir.
Is this screen visible?
Yes, sir. Slides are not visible, your screen.
Yeah, only
Yes,
screen is
sir.
visible. Okay,
Yeah, screen
so
is
this is the software what I was telling you about.
Yeah, full
This is
proof.
the software. Once you click it here, you will get this. So this I already shown you in the presentation. Now I'm just saying, I'm giving a real-time demo here. So as I told you, we are more interested on this window to open the ritual refinement software. So now this is the software in which we have to see what kind of information we can give. As I told you, if you want to do a plotting, only just select this. What I'm having this window. So what kind of input data I'm having, or what kind of data instrument is providing to you, or what kind of data you have formatted. I have formatted in this pattern. So I have taken this data. I can select, let's say, zinc oxide pure foolproof, lot of data I'm having. So I can select some data. Okay, so now I have plotted, only I have plotted. So with the left click, I can zoom it, right click, I can unzoom it. I can see background, where it is good, where it is bad, kahan sahi hai, kahan galat hai, whether it is logically, it is not logical. So with left click and right click, I can do any kind of thing. This easiness you won't find in Origin. Every time you have to do, but for final plotting, for final plotting and demonstration, you can use Origin, but here just to get more clarity, more zooming with less time, I can use this software. Okay, so this is just a first is only for plotting, nothing other than that. Okay, now here I'll tell you how to prepare a input file. As I have clicked in ED edit PCR. So this is the editor PCR. This window will appear. Now here I told you this is an inactive window. Here you won't get any information out here. So this is one of the way to prepare an input file. Another way also I will tell you later on. But with this, I'll just see, okay, once I'll say a new file, a file new, so it will prepare a new file. Here I can give my input information, what I want to give. So what I can do, what I have to do, I have to do a refinement calculation on powder diffraction profile. Okay, so this I have selected. Otherwise, if single crystal, I can do here some simulated annealing optimization. So depending upon requirement, I can give, and I can give, let's say, BTOG. Okay, so this is my file name I had given. Just BTO is my data. So G just for Gwalior. So I have to prepare BTO dash G here also. Same name if I'll give for input file, then it will be easy for me. This file name and that file name. So for understanding, but both are having same name, but their extension are different. Okay. Now what kind of pattern I am having? Again, there is nothing here. So I can add one pattern. I can add what kind of data peak I should have. Okay, so this is the format I told you, the data what I'm having in what format. Where is my data file? I can assign that BTOG. So this is my data file, this is my input file, this is my data format. Okay, apart from that, what I have to do, I want, which job I want to do, I want to do X-ray data pattern fitting, pattern calculations. Okay, with this lambda 1, lambda 2, and this ratio. So there might be some different, if you are not using copper, if you are using any other thing, then you have to change this lambda 1, lambda 2, and the ratio. Okay, but for my case, these are the lambda 1 and this is the ratio, so I will not change and I will use this one because this is for copper X-ray data. Similarly, I'll just first tab, second tab, third tab, I can see what kind of input what I'm having. Okay, so my data is pseudo Wycott. Okay, so I'm having a pseudo Wycott actual divergence symmetry. I can select that. My data is in 2 theta format. My 2 theta minimum and 2 theta maximum is there. Either you give it or it will automatically take it from your input file. So this is your input file, I told you. Here, this is written what is your first in T1. This is the step and the final. So either you give it there or he will take it from here. So it doesn't matter much. Okay. Once I'll make okay. Till now, here you can see I don't have any file along with data file, input data file. Once I will start saving this, then I will get a file with some parameters. Okay. So I'll save after this one. First, I'll complete this all, then I will save, then I'll show, I'll see here another file will appear. Then what kind of background I am having? So normally we used to do with 6 polynomial coefficient. And the origin of polynomial, what is that? This is the place here you have to give a number where there is no peak in the pattern, means from where it will take the standard of our background. So I have taken 40, 40 is this place here, there's no peak. I cannot take 39 because the peak is there. So this is not a background position. So here I have to put a number 40, 41, 42. I can put anything where there is no peak and that will become a standard for background. Okay, there is no more other mode, so I can take this. Okay, excluded region. So these are not for X-ray data. So that's why we are not taking it. Geometry, yes, I have to take that. This is the one how we are getting. Okay, so either IRF correction you took or you can take none also, so that it will give you automatically, it will take what kind of pattern is there. Okay, if you know, give it, otherwise you can give none also. Okay, so these are the all information I had given. Okay, so here you see there is no peak other than the input file. Now what I'll do, I'll just save this, whatever information I have given in general and pattern, I will save. As soon as I will save, where I will save, again I will give the path where the input data is. Then I will give the same name BTO-G, not extension, but just name will save. Now you can see this file has been created, and this, now if I'll open this you can see it is having, based on the input what I have given, it has already put it the number like that. Okay. Below this there is no number. Okay. So whatever information I had given, it has only given those number. Okay. As soon as we'll give more information, another thing will be appended in the below section. If I'll give phases, how many phases I am having? So let's say phases means what kind of material I am having. So let's say BaTiO3. If you have a doping, then you can say Ba 0.7, Ca 0.3 if 30% calcium is doped. Okay. So depending upon your composition, you can provide the information. calculated automatically how the structure factor based on the phase you are having. Then here you can put contribution to the pattern. Since we are having a single pattern, there is no need to give. If it is a multi-pattern, then you have to give. Okay. If you have two phases like barium titrate and some strontium silicate is there, then you have to give two different information. Okay. Symmetry. Symmetry means what kind of space group you are having. Let's say PM3M. Okay. This is the space group what I am having. I have given this one. So I can give that information. I can tell okay. Again, I will save. Now if I open, then you can see BATIO3 is coming, PM3M has came, and other things are started coming appearing. Okay. Based on the structure, it has already been prepared. So with this way, you can give all the information. Okay. Here, I will tell how many refinement you have to give. Let's say at every time I can do 10 cycle of refinement. If you are well aware, then you can increase to 20, 30. Okay. Then how much relaxation I told you, you better give low relaxation, 0.2. Instead of 100%, you can give 20% relaxation. So that slowly you should refine. Similarly, here you can give positions, atomic position. Let's say how many atoms you are having 3 atoms. Here I can say barium. What is the barium type? Ba plus 2. What is the position? This is 0, 0. Zero. Occupancy is 1. Right now, we are not considering B overall, so we are taking is 0. Similarly, if I want to go to another place, TI is plus 4 state, then I can make it as 0.5, 0.5, 0.5, 0, 1. O also for oxygen, O is in -2 state. What was the O position in barium titanate? 0, 0.5, 0.5. So if I zero, 0.5, 0.5. So BA is 1, TI is 1, but oxygen is 3. BA 1, TI 1, O3. So I made it 3. So these are the way I can put the parameter. Okay. So I can put a different parameter like what is the background I want to give, some value I can give. Let's say I can give anything, just number I have to give something so that it should, instead of taking 1, instead of taking 0 for nothing, it should have some number. We can give 1, 1 also, nothing. It means just to start with, instead of 0, it will start with 1. Okay. Okay. So these are the way I can do. Yeah. I can put the numbers. Where is that? Okay. This is okay. Okay. So I can give okay. Now I can save and I can see whether those informations are reflecting there or not. So now you can see this 0, 0, 0. So everything you can get it here. Okay. So in this way, you can prepare your input file. This is the one of the way. But if you are a beginner, I will suggest you take some file from someone else and start putting the limited information what you are having and do refinement like this. Yeah. So what you do, you just take some data, previous one. Since I have refined this, so I know what are the input I have to give. So these are very standard thing. I should not touch all these things. What is changing with material and space group is 2-3 things. Number one is this number, the symmetry, the y composition, the lattice parameter. Only these things you should take it from other and take the input, changes, then do the refinement. Now, I'll tell you one more thing. Let's say we have prepared this file by any means. Now you want to refine. Now, earlier I told you what will be the refinement strategy. First, you have to do refinement for a structure. Scale 0, background, lattice parameter, node background, peak width, atomic position. So now where is that? This thing I already taught you. Okay. So refinement, okay, here is already there. Refinement strategy, first is scale factor. So where is the scale? This here you can see this is scale. So here I have written, under that I have written 1, 1. The first one represent the order and second one represent whether it is on or off, or if it is 1 is on, 0 is off. Okay. So if it is 1, 1 means first parameter on, 1, 0 first parameter off. Okay. So out of this 2-digit number, the last digit is on, off, or if you are very experienced, if you are having very information about that, then what you can do, you can make on, off to semi on, semi off also. But try to forget about this thing, only on, off you consider. So, so first one is scale. So I made this number 1, then 0. You can see this is 0. Then I made it code 0, 2 on. Then background. So these are the background. 3, 1, 3, 4, 3 on, 4 on, 5 on, 6 on, 7 on, 8 on. Then lattice parameter. So what I will do, numbering I will give like that. Now I said scale factor 1 on, but here I will write only 1. How many parameter I want to define? Only 1 parameter I want to define. So whatever you give on, off, it will not read beyond parameter what is written here, 1. It will define first parameter only so that it will match your pattern. Then it will do the refinement DC square fitting. If it is on, if it is perfect, then make it 2 for 0 shifting. So 1 and 2 will go like that. Then background. So after 1 and 2, it will not become 3. It will become 3, 4, 5, 6, 7, 8. So directly with linear background and more background, we can combine, or you can go 1 by 1. Okay. That also you can do, but this parameter immediately won't affect much. So what we do 1, 2, then directly we'll make it 8. Okay. So 1, 2, 8, we'll refine 1 by 1 cycle like that. So 8, now I see the 9, 10, lattice parameter, it's a tetrahedral system. So 9, 9, 10. If it is a cubic, then 9, 9.
Screen. Some network issue is there.
Oh, so some network issue was there.
Yes, sir.
Oh, I thought I was presenting, so I was.
For seconds, sir. Yeah.
Okay. So first second was over, na?
Yes, sir.
Okay. So numbering I told 0, then your scale 1 and 2. Then after scaling, then I have to go for a background. For background, usually we go all together at a single strand, but we can go step by step like linear background. Then in second step, we can go for more background. but these two won't affect much. So we'll take 3, 4, 5, 6, 7, 8 simultaneously. So here in first cycle, first run 1, then 2, then 8, then we'll make it 9, 10. So if it is cubic, orthorhombic, or tetragonal, depending upon that, cubic, all three will be same, 9, 9, 9, tetragonal 9, 9, 10, or orthorhombic 9, 10, 11. Okay. Then UVW parameter is there. For peak width, for getting the peak width, this W parameter is there. So I can make it on off like that. The first width 11, then 12, 13 like that. Okay. Then after that, we go to either atomic position or some instrumental error like 6 sign, other lot of other error, instrumental errors are there. So there we can make it like that. So with this way, I can go, I can change the earlier profile, I can do the refinement. So this is all about refinement, one phase, two phase, other thing, different eyes. So you can see this is for barium titanate. So here what I have done, this is 95% titanium, 5% hafnium. So here occupancy I made 95.5, but otherwise positions are same. Only occupancy 95% this titanium will occupy, 5% hafnium will occupy. Otherwise, if you see, if you match this number, this will be same everywhere. In another case of barium cerate, number of atoms are 4. You can see how I have provided the numbers. So this is nothing, just mathematical arrangement. And I'll just show you one more thing. Okay. I'll just see. Once I have prepared a profile, input file, and now I want to refine, I can refine it from here. FP, numbering I had, let's say whatever I had given, I don't know what. So I don't know whether this profile is there. So just I had given a number, so refinement is going on. And now you can see, this is already earlier I have refined some zircon ZNO samples. So you can see this is my observed data and the observed data profile. So this will give the position. This is giving the difference between observed and the modeled one. And this will cover each and every aspect. So that's why you will get more accurate information of that one. So after that, again, I can open the PCR file. So this is the file in which I used to work. I can give, if I want to refine 2 parameter, I can make 2. I can make this 10 cycle. Since I have done a lot of things, so that's why I made it 50 cycle, but I can start with 2 cycle, parameter 1, 2, 3. I have put it those information. As I told you, 0, first one is a scale, then 0, then 3, 4, 5, 6, 7, 8 background. Then since it is a tetragon system, the 9 and 10, then W11, 12, 13, shape 14, V overall means temperature factor is 15. Then this is the instrumental error, 16. If any transparency or sample is not kept it properly, then this will take care of that thing. Then after that, I can feed those number here also. If it is refinable, then I can do the refinement. Once I inserted that number, I can close this value. Okay. Then I can, with FP, I can do refinement with that. If it is, I had given 10 cycle, but you can see it's after 1 cycle, because there's no change in after 1 cycle also with the input, so it will stop. So that will tell you, okay, you had already refined your limit for that number of parameter, and these are the chi-square value, Bragg factor, the number, this minimum number will give you the goodness of fit, how much better fitting you are having, what is the still scope is there. Okay, so this is all about a ritual refinement. Now I will be happy to answer any of your question. So
Thank
I'll-
you, sir, for such an insightful session. So, may I request MET IT host kindly unmute the persons who have put their questions on the chat box so they can directly interact with the speaker. IT host, kindly unmute. Dr. Sushil Pandey को unmute कर दीजिए.
They can unmute, madam.
Yeah, you
Manisha
have
ma'am, they can
okay.
themselves unmute.
Hello.
So, yes.
Yes, sir, Sushil, sir, please ask your questions.
Good afternoon, sir.
good afternoon.
Just one question, sir.
Yeah.
In the material like 15.5 pH stainless steel, I mean, precipitate and hardened steel, which are very tough to machine.
Okay.
Then for those kind of material,
Uh,
how we can proceed for XRD analysis for those materials? And the
so
second,
your
yes,
material is in what form? It's in a bulk form, correct?
yeah, yes,
Yeah. So only thing for X-ray doesn't require bulk. Every time it doesn't require a powder. It doesn't require any shape. Only thing is if you are having any place where flatness is there, the same thing you can directly hold it. So different kind of sample holders are there.
right.
Only thing for X-ray diffraction, you need a flat surface so that X-ray can diffract uniformly from your sample surface. It's X-ray will penetrate. So it doesn't matter you are giving in the bulk form or you are giving in the penetrate form, powder form. So you
Okay,
can
okay.
use your sample as it is. Only you
Yes, sir.
have to make your top surface a flat one.
Okay. Just one more question, sir. How does it differ from FDXM? I mean, four-dimensional X-ray microscopy. How does it differ from FDXM?
So those are
Simple
different.
XRD.
Yeah, that is a totally different system. 4DXM, 6DXM, all things are there. So most of the time it is for different kind of information and it is for different kind of sample, single crystalline sample where the way you had told now, your sample is like that. If you are not able to make it like a flat one, then that fourth axis will come. Okay, then
Yes.
fourth dimension will come and it will rotate your sample such that you can get diffraction, and then it will compile everything and you will get a diffraction of it.
Right. Because the issue was in my sample was that it is very hard to machine, and while going for FDXM,
Yeah.
they were
So
asking me.
four axis, 5 axis, 6 axis diffractometer are there, but
So-
they are very rare. They are very costly. They are very rare. So you have to choose a system like that. Okay, where they are having, then you can do it. This is mainly used in single crystals, not single crystalline system, but for single crystal. Single crystal are also having same issues. Although they are bit soft, but if you break it, then their property will go away. So you have to
Exactly,
use
exactly.
as it is. So those extra dimension will come to make the sample compensate for that sample surface things.
So thank you so much. Thank you so
Okay,
much.
welcome.
Any other questions from the participants? Hina Ben Rathore, sir.
Now, Ben, kindly unmute yourself. I hope there is some technical issue from her side. So, question is, she has said that I'm working on oxides material that ABO3
ABO3 type.
components.
Okay, yeah. And I have need JCPDS file or some pure compare my XRD data. How can I get it? Inside to get data, there's option of purchase PDF for it. Okay, yeah. That if you want to use JCPDS data, yes, that is there. It is paid one. But if you are doing XRD in some other system, most of the system they purchase JCPDS data along with the system. So from where you have taken the XRD data, you can request to those people, they will provide you. Huh.
So if I can ask one more question on that.
Yeah, please.
Like, see, the JCPDS data is available for most of the material, but sometimes, like we are mechanical engineers, we work on some composites. So most of the time, we don't have JCPDS for the same material. So
Yes.
in that case, how we can proceed for that?
Okay, yeah. See, For JCPDS data, like you said, PDF4 is there. So
Sir.
PDF1 was there, PDF2 was there, PDF3 was there, PDF4 was there. Apart from that, American Mineralogy Society that is there, where also you'll get lot of information related to standard X-ray data.
Right.
PDF1 to PDF2, what was the difference? The thing what was not available in PDF1 was and discovered later on was included in PDF2. So similarly, they are enriching their thing with PDF 1 to 2, 2 to 3, 3 to 4. Okay. So if you see, there are some of my data is already included in PDF4 because earlier those data was not there. What kind of data? My data was hafnium doped barium titanate. Before I was working, there was no one was worked on barium hafnium doped barium titanate. So once that new data has came, so they requested me, they have taken my data and they have included in that one. Okay. So those are the things which you will get in latest version of the thing. Again, if that thing is still not available. Now, what is the thing? So if you are working on composite system, you know you are well aware about the phase diagram of your system. How your material A and material B phase at one end material A phase is there and at second end material B phase is there. Okay. So in the phase diagram, you will see there is a continuous changes of phase A to phase B. Okay. So what strategy we apply if we don't have those things? So we see which is the major phase. If it is at the near 90% at A and 10% is material B. So we put the data while refinement, we put the information of material A. Then we do refinement. So automatically what change occurred in the system? The change occurred in the system is very nominal. Okay, my peak is little bit shifted. My peak background got little bit suppressed, but peak position is there. If there is no change in peak position, then crystal structure or symmetry changeover is very nominal. Okay, so those things you will after refinement you will get the refined parameter which is more accurate to your system. If it is near to A, I will go with A1. If it is near to B, I will go with B1. Until and unless there is a symmetry changes. If some kind of symmetry changes there, then you need a new data, then you need a new information. Then you have to work with a standard protocol is there, or there are a lot of things like microscopy or crystallography. That protocol you have to follow for a very new system, which is nowhere available. But for a normal material where you are doing some kind of compositing, where you are doing some kind of doping, then you can do the highest one with higher phases, the information you can take, and then you refine it so that you will get a more accurate with that much component, 90%, 10%, or 80%, 20% things.
So
Those
your
things will
voice-
vary. So for getting JCPD's data, madam, that you have from where you have taken the data now, just request to those people, they will provide you. They are already, most of the instrument has those data with them. Nowadays, every instrument company supply with the at least one copy with the instrument. Although since it is a cost based, so they won't give more user friendly you can say it cannot be opened in a lot of computers, but at least on the same computer from where you have taken data, it can be opened from that. Anything
other
else, madam? Any questions?
Sir, I don't think there are much questions now. Over to Madhvi ma'am.
Thank you, sir. On behalf of MIT University, Madhya Pradesh, I would like to give you my heartfelt thanks to deliver such enlightening and knowledgeable session. We are very grateful that you have given us this lecture, and we would like to have future collaborations with you as well, sir. Thank you, sir.
Thank you, madam. Thank you.